Hello and welcome to Mining Math Contests for Problems. This is sort of a condensed version of the presentation that I did for the OCDSB PD Day on February 17th. I'm going to start with some problems. Unlike on the presentation, I'm not going to give you time to do these. What I would suggest is every time there's some problems up, you should pause the video, take some time to play with the problems, think about the problems, maybe discuss problems with people. This is stuff that we want our students to do, and it's stuff that it's good for us to do as well as teachers, to actually go through the process of solving the problems and thinking about them for ourselves, but actually going to a different level for us where we're also trying to think about what the students would do and what sort of supports we're going to need for them as well. So, if you want, pause right now, work through these problems. We'll go take a look at them right away. Okay, so first problem, nice cute little thing. This is from a grade 8 contest from the Gauss contest done by the CMC at University of Waterloo. A couple of different ways that kids could do it. Sort of the most basic way they can handle it would be to say that the first possible Wednesday could be on the 1st, which would mean the second would be on the 8th, and the third would be on the 15th, and then going through and doing the same thing for the other Wednesdays. So the second, the third, and fourth down the line. And we see that the third Wednesday can't be the 22nd because the latest it could be would be the 21st. Okay. Well, we could also, sort of if the student was thinking ahead, say, well, the earliest the first Wednesday could be is the 1st, which would mean that the earliest the third Wednesday could be is the 15th. And the latest the first Wednesday could be is the 7th, which means the latest that the first Wednesday could be is the 21st. So we could kind of get to our answer there a little bit quicker. And similarly, a student could have actually said the earliest that a first Wednesday could be is the 1st, which means the earliest the third Wednesday could be is the 15th. But if I go one more step, the fourth Wednesday could be the 22nd, which actually would be the third Wednesday if we started on the 8th, but this couldn't be a third Wednesday. So this is sort of our first impossible third Wednesday. So we know all numbers from the 15th inclusive to the 22nd not inclusive are there, and it allows us to get this. And these types of problems, it's important to get students to talk about them because in some cases, students talk about this problem by saying, what did you get? I got B. Great. I got B too. Let's go on. But they could have done this very different ways. And that's where sort of the learning occurs for them, is to see each other's way of thinking about the problem, because it sort of opens up their eyes to new ways to solve problems. Second one was from a grade 9 contest last year. Again, several ways we could do it. One way we could do it, we could look and say there's 18 tasks in total. We want to share the tasks, so that means that everybody has to do 9 each. Robin already does 4, so she needs to do 5 more. Okay. We could also do it a different way. We could look at it at Robin has to do hers first. When she's done, Sasha's already done 4, so she's got 10 left. So we could just divide up what's left to find out what Robin's is. And if we start thinking a little bit more convolutedly, we could say, well, if they're going to do equal amounts, we could do that by basically saying, I'll do half of yours and you do half of mine. So when Robin's done, she's going to do half of Sasha's, But Sasha would have already done half of hers, so we can take off those ones that Sasha's going to do to leave us with 5 more. Okay, so those 2 problems were warm-ups. The next problem I call sort of a neat problem, where we've got these box of candies, and we're going through this process of eating half of them and giving one to our sister, and eventually we run out. This is from the Canadian Open Math Challenge, and thinking of it as I would think of it, I'd probably think of this algebraically. So I'd say let n represent the number of candies that he starts with. So after the first day, he's going to divide by 2 and subtract 1. So that's how many he has left. The next day, he's going to divide that by 2 and subtract 1. The next day, he's going to do it again. And since he's got none left, we know that this expression is 0, and I can solve it to get 14. So a nice little exercise in algebraic reasoning. And the 4th problem, this one's kind of neat because it's really just a subtraction question, but it's a subtraction question from hell. Like, we've got 500-digit numbers that we're going to have to subtract. And we have to sort of think about, well, how could we go about doing this? And this is from the Canadian Team Contest, the individual problems. So, first way I looked at it is I looked at these powers of 10 and sort of found a common base by writing this 3 times 10 to the 500 as 3,000 times 10 to the 497. And then we can gather some like terms and simplify that to a big power, a number times a big power of 10 minus something else. And now, how do we deal with this? Well, we can deal with it by thinking of it in terms of how we would do a regular subtraction question. Except now, instead of writing things out, we're going to have to sort of describe it. So this first number is 978, followed by 497 zeros, and we're subtracting this guy down here. Now, how would we handle that usually? We'd go 0 minus 2. Oh, I can't do that. I'm going to have to do borrowing, 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 borrowing. So what happens? I borrow from that 8. It becomes a 7. This becomes a 10. And I borrow one. It becomes a 9 and a 9 and a 9 and a 9 and a 9, all the way to a 10. So originally I had 497 zeros. I end up with 496 nines and a 10 at the end. And I can sort of think of this as 2 separate questions. That's the 10. I'm just going to subtract those 2 things now. That gives me 7978. And over here, there's nothing left, so that can just pop down. And as a result, now we've described what the answer looks like, so we can go and do the sum digits. So, before we go any further, when I did this presentation, my original intent was to do all the problems from 2022 of Canadian contests that are available online. So these are all things you can just go online, you can download the contest, and you can get the solutions. Now, most of you will probably be aware of at least some of the contests from the CEMC at the University of Waterloo, Pascal, Cayley, and Fermat, the multiple choice question problem contests for grade 9, 10, 11. You probably heard of the Euclid, maybe Friar Galois, Hypatia, or some of these other contests. I'd also looked at the ones from the Canadian Math Society. They have a multiple choice contest at the grade 8 and lower level called the Canada J. They're in the process of working out some other ones at the high school level. I also looked at the Canadian Open Math Challenge, which is set at the grade 12 level. There's one question from that in my presentation, but the rest of it is from the CEMC. Just because by the time I'd gone through the CEMC material and pulled out all the stuff that I found interesting, I already had 14 pages worth of problems to look at, and so it was starting to become overwhelming. But just to show that there's lots there, lots just from Waterloo, we've got some other ones here, and these are all other Canadian contests that are available online, that you've got years and years and years worth of stuff there to pull problems. And then if you want to go into other contests, I've got sort of in this handout various other things, and I'll put a link in the video description to this. But for the most part, other than the last question that we looked at, pretty much everything comes from one of the Waterloo contests or another. So let's go back to this. Okay. So let's revisit that question with the candies. So we went through and solved it algebraically. We could check our answer by actually going through and saying, well, if we start with 14, we eat half, that's 7. We give one more away, we'll be left with 6. Eat half gives us 3. One more gives us 2. Eat half, that's 1. Give one away, it's 0. That works. But it's always nice to think about sort of questions that come to mind afterwards. And a question that immediately comes to my mind is, well, here we started with 14 and we ended up with nothing. Sort of trivially, by the way that we solved it, if I started with 6, eventually I would end up with nothing. If I start with 2, I'd eventually end up with nothing. But what else could I have started with that I eventually, after a certain number of days, would have ended up with nothing? So the key to that is the statement that we saw sort of on each day, that on such and such a day he ate half of his candies and gave one to his little sister, which is the thing that we're doing over and over again. So we have what he had at the beginning of the day, what he had at the end of the day. We saw that to go from there to there, we're cutting it in half and then removing 1. So if we think algebraically, if the start of the day is x, then the end of the day is going to be x divided by 2 minus 1. And that rule, C, will move us from our 14 to our 6 to our 2 to our 0. But to keep going back, we might think, well, instead of having the arrows go this way, can we have the arrows go the other way? And the beauty about this problem, even though we can think of it in terms of inverse functions for students at grade 11 level or above, for a grade 9 or below student, they can actually think about the reversing process without the idea of an inverse and say, well, if going from here to here is cutting in half and removing 1, if we think of this as we're watching a film and it goes 14 to 6 to 2 to 1 and we're cutting in half and removing 1, cutting in half and removing 1, if we played the film in reverse, we would see undoing this remove 1, which is adding 1, undoing this cut in half, which is double. So to go that way, we're going to add 1 and then double our result, which means that if I call this y, then I'm going to add 1 and then double the result, including that 1 that we just added. So if we see what happens, if I start with 0, add 1 is 1 and double is 2, add 1 is 3 and double is 6, add 1 is 7 and double is 14. So it seems to work. And if we keep going, 14 and 1 is 15, double is 30, 30 and 1 is 31, plus double is 62, and so on. So we can see down the line. So the next thing becomes, well, is there another way we can describe this? And if we get up to grade 11 and beyond, where we do sequences, we can see that this is just the definition of a recursive sequence, where we've said, okay, I know how to get from one step to another. There's my rule. And if I start with 0, there's how we do it. And so this could generate things to the cows come home. But if we wanted to find out what we'd have to start with on the 100th day, we probably don't want to go through this process. So we want to look for some sort of a closed form formula for this. And actually looking at the 14, 6, 2, and 0, it might be kind of hard to see what's going on. But when we start getting out the 30, the 62, the 126, and especially if we keep in mind that we're doubling every time, so I'm multiplying by 2 over and over and over again, I start thinking powers of 2. So what are the powers of 2? Oh, 2, 4, 8, 16, 32, 64, 128. It seems that I'm 2 lower than powers of 2 at each case. And if you plug that in, we see that we can actually come up with a formula in terms of powers of 2 for our closed form formula for this sequence. And on top of that, we can even go one step further, and even though we don't teach induction, we can show that if we use this formula in our recursive sequence, you plug the y, if I put n minus 1 in here and plug it in, I'm actually going to get out my formula for yn. Okay. So I kind of think of, well, let's look at the structure of many math contests. So one thing that's important, this will sort of help you, guide you when you're looking for problems for your classes. A grade X contest may or may not contain any material from grade X. So for instance, from the Waterloo material, the Cayley and the Galois are grade 10 contests. You're not actually going to find any grade 10 material on those contests. There's going to be nothing that's going to involve quadratics or trigonometry or any of that kind of stuff. And the reason for that is just when these contests occur. The Cayley occurs in February, which is right at the start of semester 2. So a student in the second semester wouldn't have seen any of the course. So as a result, the contest, to be fair, is basically everything up to grade 10. So for you as a teacher, if you're looking for some quadratic stuff for your grade 10 class, don't look at the grade 10 contest. You're going to have to look at grade 11 or grade 12 contests. Questions go from easy to hard. That kind of makes sense. But keep in mind that they go from easy to hard, in the sense that a contest is meant to be a challenge for students. So you might think, oh, okay, well, I can't use a lot of those questions for in my classes. But if we look at the easiest question, this is question number 1 from the grade 11 contest, which you should be able to give to even somebody in grade 7 and 8, and they should be able to do it. There might be mistakes, but this is well within their knowledge range. And if you look at the first sets of questions, they are usually very straightforward. And the philosophy of the contest maker is the first question, you want to engage the kids. You want a lot of them to have success in the first questions, and you want it to gradually get more difficult as we go along, so that there is something for everybody to have success with at the beginning, and there's going to be something for everybody to be challenged by as they go later on in the contest. On the other end, this is the last question from the grade 9 contest from last year, which if you look at it, it's quite involved. And you could probably give this question to a lot of your grade 11s and 12s, and a lot of them would have problems doing it. Not because the math is overly difficult, it's just there's a lot of stuff you have to sort out here, and there's lots of little intuitive steps that you have to make, and different parts of mathematics that you have to piece together. So as it stands, question 25 from a grade 9 contest, you probably wouldn't want to give to your grade 9 class, because there would be few, if any, of your students that would be able to do it. However, that doesn't mean that it's useless to you as a grade 9 teacher, because you can use this as inspiration and say, okay, well, if instead of a hexagonal prism, let's deal with a square-based prism. Let's still have the fly going from one corner to the opposite corner at the top. Let's have the ant going around, but instead of n plus a half times, you could have it go around either just a half a time, or maybe even just 1.5 times, and compare that. Or you could change this from 20 times down to 2 times, or something that takes the idea that was here and just makes it a little bit more approachable. Or even break the problem up into parts and just basically say, well, if the ant crawls from here to here, how far does he go? And then introduce the, well, now if he goes around 1.5, how far does he go? And 2.5, and how can we go and look at that? Questions on math contests tend not to be textbooky, and by this I mean when you look at a question from a section of a textbook, there's something particular that section is dealing with, and so all the problems deal with that, and are exercises on having students practice certain skills. And so that's why if you look at your textbook, it's quite easy to look at 8 or 9 or 10 questions from a very fundamental standpoint and say, you know what, these 10 questions are asking the same thing. There's different contexts, there's different numbers, but they're all asking the same thing. Find the vertex of the parabola or whatever. And you won't find many, well, you find some, but most questions tend not to be like that. They tend to be a little bit more novel. Having said that, sometimes you'll get questions that will be contesty. For instance, if you think of our big subtraction question that we did, why are they asking us to add all the digits of the number? Okay, we're really interested, the question's really interested in, can you actually figure out what the result would be, right? Can you actually do that and describe what the number would be that you would end up with? But in order to have an answer that we can mark, we have to take that big thing, because you don't want to be writing down a 500-digit number or whatever it was. You want to have something that we can write down and check easily. So they take the answer that they want and they create an answer that they can mark. You'll find the same sort of things for multiple choice questions, where you can take a question that's really difficult to do, but if you present somebody with the answer, they can easily look at an answer and reverse engineer to see if it works. So you can take a really tough question that if it wasn't multiple choice, it'd be hard to do, but if you make it multiple choice, it becomes trivial. So now if it's in a multiple choice question, you could say, well, instead of giving them the answer, we could say something like add the digits, or something like that, where you're mixing things up so that you're not really presenting them something that they can work backwards from, and sort of make it much easier. So keep that in mind, because when you're presenting it to your classroom, you might just sweep that contesty thing away. And Sometimes contests at grade X can be used at grade above or below grade X. So for instance, here's one that jumped to mind. That's dealing with this cube. This was on a grade 10 contest. And like I said, when I go through and do contests, first and foremost, I do it as me. And sort of the first thing that comes to mind is me. And then usually I'll go back and look at different ways that it can be done. And I'll start thinking in terms of how would a student do it. And when I did this problem, I did it totally using vectors. I set up a cube in three-dimensional space where all the vertices coordinates are zeros or ones. For this diagonal pointing up to the sun, I basically thought of the diagonal through 0, 0, 0, 1, 1, 1, which meant that my ground, that's going to be the direction to my sun. So my ground is going to be perpendicular to that. So this is basically the normal to my plane. So 1, 1, 1 is going to be normal to my plane. So my plane is going to be x plus y plus z equals something. If it goes through 0, 0, 0, it's going to be x plus y plus z equals 0, 0, 0 equals 0. And now I can just do projections of all the other points onto that plane. 1, 1, 1 we already know is going to project onto 0, 0, 0. But the other vertices, the other 6 vertices, are going to project to give us that hexagon that we're interested in, and we could do the problem that way. So this would be an interesting problem to actually give to your calculus and vectors kids. And as such, it's not going to be an easy problem for them. I would suspect that a lot of them wouldn't be able to do it. But if you had them in groups and you had groups sharing things, you might be able to turn this one question into a whole class, and by the end have a couple of solutions and have kids talk about it and understand what's going on. Okay, so I tend to think of contest questions when I'm thinking of them for use in my classroom. I sort of have 3 categories in my mind. The first category is something I call warm-ups. Warm-ups tend to be questions that I could throw up at the beginning of class or at the end of class that, when kids come in, they have something that they can engage themselves with, whether it's while you're doing attendance or something. You can have them look at this. The intentions of these questions are they're not too involved. If you could solve it, it shouldn't take you too much time. It's not going to be like a page and a half of writing. I think of these from a couple of points of view. I think of it from a curricular point of view as something like the first one. If you're doing lines, this is a nice way to just practice those skills of dealing with lines and equations of lines and how they go. And I may or may not remove the multiple choice things because that gives us another way of using these questions. Removing the multiple choice options can sometimes make the question a little bit more difficult. Another way that I would use it, and that's sort of like this guy here, I might think of it in a non-curricular way in that this question here, which came from a grade 12 contest, I could use with a class that are dealing with fractions right now, and it'd be a nice practice. But I could also see myself putting this up at the beginning of a grade 12 calculus and vectors class. Why? Because even though they're in grade 12, there's going to be some students in your class that aren't proficient with this skill. And as a result, there's certain things that they're going to do in mathematics that are going to be a little bit harder because they're not proficient with fractions. But if every now and then we do these little problems and they get to practice it and they get to see things, they might sort of be able to, over the years, sort of improve their their skills and their understanding and their comfort level with these types of things. A third type of problem is totally sort of a problem for the sense of a problem, in that just sort of getting them thinking outside of the box. Now this one, when we discussed in class, we talked about how would students solve it. Again, if we think of us solving it, or even a student that has some comfort with algebra, we can set this thing up algebraically where V is the volume of the jug, and we can go through and say, you know, a quarter V plus 24 equals 5/8 V, and solve it that way. But I challenge you to think about how kids might think about it. And, you know, kids might think about this like in terms of manipulatives, depending on the level that they're at. Or they might think of it pictorially, where they kind of write out a number line and mark off 1/4 and 5/8, and they think, oh, 5/8, I got to mark it in 8s. Oh, this is going to be 2/8. And then you can see from our marking off that from here to here is 3/8, and that's going to be 24 liters. Well, actually from here to the end is 3/8, and that's another 24 liters. And from there to the beginning is 2/8. Well, if this is 24 and that's 3/8, you know, we can get 1/8, and we can work out it that way. So again, there's lots of different ways that we can handle this. And this one kind of made me think a little bit of number talks, where the different ways that people can do the problem is enlightening, because one student may do it one way, one student may do it another, and sort of through that sharing and discussion, they might learn something from each other. And so these warm-ups are a great way to do that. And again, they're not meant to be big involved things. These are meant to take up, you know, a couple minutes at the beginning or end of your class. And there's tons of them. Second type, I kind of think of these, classify these as neat problems. And again, these are not distinct sets. In a lot of cases, things from the warm-ups could be used here. Sometimes these could be used as warm-ups. I think of these as, again, they can be curricular or non-curricular, but I think of these as either something you might put into a homework assignment or something like that, or maybe even on a test. And again, they're just have a slight twist to them. So if we look at something like the last one, guaranteed, if you give this to a student in grade 10 who's seen linear systems, or a student above grade 10 who's seen linear systems, most kids are going to either, you know, do substitution or elimination and solve this for x and y, and then add x and y together to get our answer, which is great. But some might look at this and say, well, I'm after x plus y. I've got 10 x's and a y and 10 y's and an x. If I add these two equations together, I get 11 x's and 11 y's equaling 132, which means I can divide by 11 and get the answer without actually knowing what x and y are, which is really powerful. And if somebody comes up with that and others see that, they might go, wow, like it just opens a door where you try to get kids to keep their brain alive when they see a problem, and not necessarily look at this and go, oh yeah, I'm falling into systems of equation mode, what steps do I go through, and so on and so forth, and never really engage the brain. And if we think a little bit further, somebody thinking further might say 10x plus y, 10y plus x. This kind of looks like how we write our decimal numbers. And 10x plus y, 10y plus x, it's like I'm switching the tens and the units, And if I look at my numbers, 75, 57, the question actually gives it away. This actually tells us x is 7 and y is 5. So you could actually get the answer immediately by just recognizing this as the decimal representation of 75, or the expanded version of 75 and 57. So lots of cool things to go there, and that becomes important for algebraic modeling and so on, and then almost thinking of numbers in an algebraic sense. And before I go into my last classification, I'm going to talk a little bit about problem solving a la Polya. George Polya was an American, Hungarian-American mathematician who in the 40s wrote a book, How to Solve It, which was kind of the first treatise on mathematical problem solving. And if you've ever seen methods when they say, oh, you go through these steps in solving a problem, it's all basically going back to what Polya did in How to Solve It. And he basically breaks it down into 4 steps. First thing you have to do is you have to understand the problem. If you don't understand what the problem's asking or some of the things that are in the problem, it's going to be impossible to solve. Next thing you've got to do is create a plan, whether you actually jot down a plan or it's just, oh yes, these are the things I have to do. And you might, depending on the complexity of the problem, do step 2 and step 3 simultaneously, which is carry out the plan. You know, if it's a fairly easy problem, you kind of are creating and doing the plan at the same time. Whereas if it's more involved, you might say, oh, we might try this or might try this, or so on and so forth. And the last thing, you reflect on the result. And realistically, when you go through this process, you can always think of all of these steps having backwards arrows. So when you think you understand the problem, if you create a plan and you go to carry it out and you don't get anywhere, well, you could fall back maybe to create a plan and do something different, or you might go back to see if there's something you misunderstood from the problem, and so on and so forth. I always find this last step to be one of the most important. Sometimes it's overlooked by the kids. At the very least, it means, does your answer make sense? Should we check to see if our answer makes sense? Is there some way we can do this? That's one important thing to do. But there's more to that we can do at the end. Another really important thing that we can think about is there another way we can solve the problem? Because if we can solve the problem in multiple ways, get the same answer, it makes us think we've got a lot of confidence in our answer. The second thing is that it will also sort of give us some insights into things. So different ways of solving problems sort of give us different insights into the situation that we're dealing with. And in some cases, just getting kids to talk to each other can help them see these other ways to solve the problem, see which way is best, and things like that. You can get useful conversations going on that way. But it's also important to think about, how do we think like a mathematician at the end? And that is, can we actually take this problem and not think about the answers being the end? Can we extend it to different cases? Can we generalize it? Or is this something that just worked for these particular numbers or situation that was given to us? And the all-important what-if questions that sometimes we think, or we should force ourselves to say, what would happen if instead of asking this, we ask this? And it's really good to try to train kids to think about these types of things, and also not only come up with these questions, but then try to answer them themselves. And this kind of leads to my last type of things that I think of when I use these problems are places where we can use for investigations. And here's a question from last year's grade 9 Pascal contest, where we've got these 5 balls in order 1, 2, 3, 4, 5 on the desk. And we've got these 2 things that we're doing. Sort of step 1 is take the ball that's at furthest on the right and you put it in between the remaining 4. So the 5 goes between 1 and 2 and 3 and 4. And the second step is you take the one from the left and you do the same thing. Put it in the middle. So the 5 goes in the middle and then the 1 goes in the middle. And then you just repeat the process. The 4 would go between the 1 and 5, and then the 2 would go between that, and you keep going. And it says if you keep doing this, eventually the balls are going to be in reverse order. So we started 1, 2, 3, 4, 5. At some point it's going to be 5, 4, 3, 2, 1. And it says when of these is that going to happen? And again, this is a little contesty because it's going to happen a lot. We know from this all we're doing is we're permuting the balls in specific ways, and we know from 5 balls there's going to be 5 factorial or 120 different ways to permute these balls, which means that the worst case scenario, if I keep doing this, after 120 goes, I should be back to my start. That this thing's going to eventually hit something I've seen before, and as soon as I hit something I've seen before, I'm just going to go into a loop. So these numbers are all bigger than 120. It tells us I'm going to hit the reverse order. It means I'm going to hit the reverse order a lot of times. Now, if we just do the problem and think like a student, or I sort of channel my inner youth, this might be how I would do it. I would say, okay, let's do the first step. The 5 goes there, then the 1 goes there, then the 4 goes there, then the 2 goes there, then the 3 goes there, and it's reversed. Oh, it's reversed after 5. That means that it's going to reverse every 5. Oh, okay. Well, so it's going to go multiples of 5. If I look at my answers, I can get rid of this guy, and this guy. I'm left with 20, 20, and 20, 25. Oh, it happens first right there. So there's going to be my answer. And I'm done. Yay, hooray. Let's go on to something else. Now, if the student is a more methodical thinker, unlike my younger self, they might say, what happens if we keep going with this process? If we keep going with this process, we see after 10 moves, it's reversed the reverse and it's back to its start. Or if a student is thinking, they might think it takes 5 steps to reverse, which means if I start here, after 5 more steps, it's going to reverse the reverse and it's going to be back to its start. Which means that after 15 it'll be reversed, after 20 it'll be back to start, 25 it'll be reversed, 30 it'll be back to its start. So we see that every number that ends with a 5 it'll be reversed, every number that ends with a 0 it'll be back to its start. So here it's not actually reversed, it's actually in its original order, and our end result is here. Now, in a contest, you'd go on to the next question. But here's where we should stop and think about this and ask ourselves some questions. That's kind of neat that if you have 5 balls and you go through this process, it will reverse. I needed an odd number of balls so that when I picked up 1, there was a middle to put that ball. So if I started with 3 balls, would it reverse at a certain point, or would it just go back to its original? What about 7? What about all odd numbers? Can this thing work for all odd numbers? Can I adapt my process for even numbers? So if I had 4 numbers, when I pick the one at the end, there's only 3 left, so I can't put it in the middle. So I either have to put it between the first and the second, or the second and the third? Will one of those eventually give us a process that will reverse things? Can I do something else that will reverse the order and come up with an algorithm that will do that? And then you can start thinking about what's the best. Especially with coding in the classroom now, this idea of an algorithm, now we can maybe even test it out and write a little program that would do something like this. This idea of best algorithm becomes an important question to ask. In one of the columns that I write for the OME Gazette, a recent article that I did, I looked at a problem that I talked about writing a program to solve it. It was finding numbers where if you do stuff to their digits, you end up back with a number. It was 8-digit numbers that if you raise each of the digits to the 8th power and add them all together, you get the original number. So I had started by just writing 8 loops that go from 0 to 9, running it through and seeing if you get back to what you started. And it pops out an answer. But it's not an efficient algorithm, because if you want to do that for 100-digit numbers, your program will never get done. Okay? But I go through and talk about how to use some logic and thinking about the problem to be able to adapt our algorithm so that we don't have to check all the possible cases. We can use some reasoning to fine-tune what the algorithm checks, and thus sort of come up with a better algorithm. Okay, some things for you to consider when you go to create investigations and using problems in your classroom. How can I adapt this so my students can engage? In some cases, you may be dealing with a really difficult problem. Can I use simpler numbers? Can I use a different context? What do I have to do to get them to deal with this? Can this problem be extended or generalized? If you're setting it up for investigation, it's good that there's other places to go. That it might take some groups or some students less time than others to do it. So it's nice if when one group or set of students is done, there's other directions that you can nudge them to go. How are the students going to solve this? Do you need to have Chromebooks around so that they have access to graphing calculators or spreadsheets or coding, or do you need manipulatives, or what types of things? So make sure you know these things so that the students have what they need to solve the problem. And what sort of questions can arise that will sort of lead on their investigations. And it's one of those things that you're going to have to probe the kids at the start to do this and model this for them, of you saying, I thought about this and I thought about this, and then how could we investigate those, and getting the kids to do that as well. So originally, we kind of ran out of time with this, but this was 2 problems that I gave for people to think about in terms of investigations. If you want to think about this yourself, go ahead. I'm going to talk about them very briefly in a second. So you might want to pause if you want to think about it. First one's kind of cute. It's got this 64 cubes. Each cube has 6 faces, labeled with 2 on one side and 1 on all the other 4 faces. And those things, so you're basically having dice, but instead of having 1, 2, 3, 4, 5, 6, they have 2 2s opposite sides, 1s on the other sides. You take 64 of these and you make a 4x4 cube, and you want to find what total could be on the outside. Really cool question. thinking about how you can adapt this for your students, well, instead of having a 4x4x4, you could think smaller, 3x3x3, or 2x2x2. You could think of the natural place to extend is to bigger. Can you come up with describing it in general? So that for an n by n by n cube, you can actually come up with a formula that will say you're going to get between this number and this number. You can adapt your cubes or your dice to standard dice. So 1, 2, 3, 4, 5, 6, where opposite sides always add up to 7. That might be a lot more interesting a problem to deal with. So lots of different ways that you can go with this one. This one is part C and part D of a question from Hypatia, which basically created a sequence by having a function and iterating the function. So you start with a number, you run it through the function, you get an answer, you take that answer, you run it through the function, and so on and so on and so forth. And part C basically dealt with a fixed point for this. In other words, you plug something in and you get the same result. And again, you could take this in all kinds of directions and think about, do all quadratics have fixed points? What is the relationship between this and other properties? Can we tell just by looking at this if it's going to have a fixed point or not? It's interesting to see this geometrically, because really what you're if you want to look at this geometrically, you're looking at y equals x and y equals this thing crossing. Where are those two things going to be the same? And so we'd see that fixed points are actually the intersection of this thing with the line y equals x. And at one point, I think I had given a question on one of my calculus tests that basically was related to this. And because then, if you're thinking in terms of the calculus kids, you can talk about tangents. And if the line y equals x is tangent to your parabola, then there's only going to be one fixed point. And if it cuts in two places, there's going to be two fixed points, and if it misses, it's going to have none. And then part D goes to, instead of having a fixed point, you're getting a series of values where if you plug one number in, it gives you a second number. If you plug that number in, you get back to the first. And again, you can go through the same sort of idea. Do all functions, quadratic functions, have sort of these ABs that go together, and how are they related to it? Is there an ABC that works? Is there other types of things that work? This sort of leads in all kinds of different directions. And depending on the level of the students, they can attack this. If they've got tools like calculus, they can attack it in a very different way than if this is a grade 10 class. Whereas in a grade 10 class, we could actually attack this with something like Desmos. And if you had grade 11 where you had function notation, and you could look at that idea of composition of functions where we're doing f of x, you can start looking at things with it as well. And again, lots of different ways that you could take this thing. Okay. Before I finish off, I wanted to do a couple of shameless plugs of things that I do. I in no way get money for any of this stuff. This is just stuff that I do that's of interest to teachers and to students. And I just want people to be aware that this stuff is out there. This is out there for free. And please check some of these things out. For one, I read a column in the OME Gazette called What's the Problem? Basically, 4 times a year, every time the Gazette comes out, each issue has one of my articles. And basically, I look at one problem. I dissect it from the point of view of how this could be used in a classroom, how different ways that it could be solved, and stuff like that. I've been doing it for many years now. I think I'm in my 17th year of doing this. So if you go to the OAME website, I think you have access to all of the back issues of the Gazette from a certain point on. I don't know how many years. If you're a member, you have all years. If you're not a member, I think it's 3 or 4 years back and back. It goes back to the 60s, so there's lots of material for you. The Saskatchewan Math Teachers Society, actually somebody had read one of my articles and asked me to write for them, so I did basically the same idea for them in their journal called The Variable. Now their journal just folded a little while back, but they have like a newsletter that they do online, and actually now I've been sending them articles for their newsletter, and they've actually set up a part on their website for my articles, and those are all available for free. That's the same idea as the first one. Mathematic is a section of the problem-solving journal Crux Mathematicorum. Crux Mathematicorum is a problem-solving journal done by the Canadian Math Society. It's available for free on their website, and you've got the 40-some years worth of it. If you go back to year one in 1975, the journal was actually set up by COMA, the Carleton Ottawa Math Association, back then, as a newsletter for the teachers, and where they presented problems and little articles and that for teacher enrichment. And somehow it got to be known internationally and became an international journal. Now the problems in Crux are way beyond what you're going to be able to use in the classroom, because it's just gone a little bit nuts. But there's been various times that there's been sections for high school students, and sort of this mathematic section, which here you see is like 21 pages, is all devoted to high school students and teachers, stuff that's of interest to them. And if you look at it, I do a column called Problem Solving Vignettes. Crux comes out 10 times a year, every month except for the 2 summer months. It follows the school schedule. This is more aimed towards students that might be interested in doing contests, but there might be stuff that would be of interest to teachers as well. My column alternates with one called Teaching Problems. That's done by my colleague John Grant McLaughlin, who's a prof at the Faculty of Ed out at the University of New Brunswick. And these are specifically questions that can be used to teach concept in classrooms. And so I do 5, he does 5 a year, and they alternate. We have another feature called From the Bookshelf, which is basically book reviews, but they're book reviews in the sense of people do reviews of books that they really enjoy that are mathematical in nature. So rather than publishing companies sending us books to be reviewed, people are coming forward and saying, this is a math book that I read that I really liked, and here's all about it. So there's stuff of interest to people if you like mathy type books. Mathematics from the web, so just sort of podcast videos, articles that you can find of a mathematical nature that are available on the web. So just sort of little 1-paragraph things, and these 2 are in each issue. A new column that just started, Mathemagical Puzzles, is every second issue, and it deals with puzzles and sort of the mathematics behind them, done by a former teacher who has designed puzzles that he's got commercially made, and he's big into puzzle stuff. So that's a very interesting column. Each issue has problems that are meant for the people that are reading it to solve. And so each issue has 5 questions. Readers can send in their solution, and about 6 issues later, the solutions up from the readers are presented. And we get the occasional article. And we're working on a column on cultural mathematics. We had a couple of columns done. The person that started the column wanted to do indigenous mathematics, but he's only been able to sort of give us, he's been really busy, and he gave us one year and one the next year. And we're looking to sort of beef this up to indigenous and other, basically cultural mathematics and ties to mathematics. So that's free. We're looking for this to get into the hands and the eyes of teachers and students. So check it out. If you've got kids that are interested in math, please let them know about this. We're interested in people that are interested in working on it and sending us stuff too. So if you're interested, you can fire me an email. Second thing, Taste of Mathematics series by the CMS. Again, this is a series of booklets that were meant as enrichment for high school students. The CMS used to sell these for like $10 or something like that, and they're like 60-page little booklets. But we're just going to the point where all of the booklets are going to be available for free online. So this is the series here. We're up to volume 17, and there's the PDF for it there, and you can sort of get the descriptions of all the other ones. Lots of them are contest collections, so this would be of use to teachers. And there's the PDF that you can get for that. Not all of them are up on the website yet. I don't know why I've sent them to them, but they should be up there shortly. Okay. And I also have a YouTube channel, Mathematical Mishmash. I do a number of things, math shorts. I try to do it monthly, but I've been kind of busy lately, so it'll come out as often as I can, and these are meant to be aimed towards stuff that students could understand. They're supposed to be short. I'm still finding my way with that, because sometimes I get carried away and I go on and on when I should have stopped, such as in this case for this video. But you can check those out. I also do a couple of teacher talk ones. Those are more involved, and those are more on topics that go beyond what we would do in school, but are related to stuff that you should or might know. I'm going into more depth just for your curiosity, and possibly for stuff that you might use in class. And I do occasional videos that tie to my columns that I talked about up here. So sometimes I'll do a techie thing in one of these, and then I'll actually go and do a video that shows you how to do the techie stuff that I kind of talked about. So if I do something on a spreadsheet, in the article I'll kind of assume that you know how to use spreadsheets, but I'll do a short video that shows you how to do the stuff on there, so you can check that out. So I'll finish off with a couple of challenges for you. I challenge you to commit some time each week solving some math contest problems yourself. So whether it's like 10 or 15 minutes, say, you know what, I'm going to spend 15 minutes a week, Wednesdays at lunch, I'll sit down and do a couple of math problems. Because you'll benefit from going through and actually doing it yourself. When you look at a problem, sometimes you'll get some ideas of what the students will do, but the more you dig into it, the more the juices get flowing and the more you're going to get out of it. Second thing, discuss the problem. See if you can find a friend that's interested in doing this with you and do it with them. Last semester, I had worked with a few of my colleagues, my former colleagues back at Crean Wilson, where I taught for many years, and I would send them some problems from math contests. They'd take a look at them, and then maybe about every second week we'd do a Zoom at lunch. We'd talk about the problems. They'd say, oh, this one was kind of cool. We kind of used it in our class, and this is how it went. Oh, this one we used with the math club. And I think there's a lot of benefit from that. So find a friend, talk about these problems. Again, it's the whole reason why we get kids to work in groups. Yeah, the sum is going to be more than, you'll get more than the sum of the parts type of thing from that. And be better than me in the sense that I was usually never organized enough to put these things aside and collate them so that I'd find great problems and I'd use it, and then I wouldn't teach a course for a couple of years, and then it'd be like, oh yeah, I had a problem, I don't remember where that is, and then I have to go and find other ones along the same line. Quit popping up. So create yourself some banks, and that's where sort of having some friends would help with that, and have some fun with this. If you can find fun in doing math problems, it's easier for you to spread that with the kids. So, hope you enjoyed this. If you have any questions, by all means, fire me an email, and happy problem solving.